So here we go with lesson 8.1. As I mentioned before, really this is just Pythagorean theorem. Nothing new. You guys have probably seen this 100 times, but we're just going to hit it one more time and call out a few conclusions that we can make using the Pythagorean theorem. Some additional applications that we can use. But to get us started off, again, this is just your basic Pythagorean theorem. So you've got a right triangle. It must be a right triangle for Pythagorean theorem to work. And that's the big issue that we've been having recently, is that we've been using a lot of triangles that are not necessarily right triangles. So it must be a right triangle, so we either need to have this symbol here, we need to be able to somehow determine that it's a right triangle. And if you have a right triangle, then the squares of the lengths of the legs are going to be equal to the square of the length of the hypotenuse, right? That's your basic definition of Pythagorean theorem. So we get A and B are two legs, so A squared plus B squared equals C squared. So the converse of this, and I know you guys talked about this term converse at the beginning of geometry, and it's really just the opposite, right? If we switch everything up. So instead of saying if we have a right triangle, then A squared plus B squared equals C squared, the converse would be the opposite. So the converse of the Pythagorean theorem would be if A squared plus B squared equals C squared, then we have a right triangle. So it's just looking at this in the opposite direction. If the square of the length of one side of a triangle is equal to the sum of the square of the lengths of the other two, then the triangle is a right triangle. So you would use the Pythagorean theorem if you're given the fact that something is a right triangle and you're trying to find one of the three sides. You would use the converse of the Pythagorean theorem if you were given three sides of a triangle but you were not told that it's a right triangle. Right? You could plug the values in for A, B, and C, and if this all works out appropriately, then we can conclude that yes, it is a right triangle. So it's just working in the opposite direction. Two more theorems that we're going to look at have to do with when things deviate from being right triangles. So right triangles are very nice. They work out. The math always works out nice and neat. We can use Pythagorean theorem. There's lots of different theorems and postulates and things that we can say about right triangles. But when we deviate away from right triangles, things get a little messier. These next two theorems look at when we do deviate slightly away from 90 degrees. So the first one just says if the square of the length of the longest side of a triangle is greater than the sum of the squares of the lengths of the other two sides, then the triangle is going to be obtuse. Now, let me show you how that works. If we're going to switch over to the camera here and take a look at, I have sort of a right triangle set up. So here we've got, let's say that this is a right angle in here between the two pencils, and we're looking at the length here of the hypotenuse. So the hypotenuse is represented by the ruler, and the way I have it set up, it looks like, I know it's hard to see because it's backwards, but I've essentially got it's at about 27 centimeters. Okay, so right now it's at 27 centimeters. Now, if I were to deviate from 90 degrees and make my angle bigger, so if I were to move the pencil so that they're no longer at a 90 degree angle and they're bigger, I'm going to pull the ruler away here for a second. But if I'm starting here at 90 degrees and I make this angle bigger by pulling this side out, notice what's happening to my length now. If I were to go back in and measure with my ruler, I'm now at almost 30 centimeters. So we should be able to see that as this angle, right, as we change this angle, so we started at 90 degrees, and here's our measurement. And as we deviate, as this angle gets bigger or becomes what they call obtuse, then the length of the hypotenuse gets bigger. Notice my legs are the same. I'm still using the same two pencils. My legs are the same, but my hypotenuse has gotten bigger as my angle gets bigger. So that's the key behind these two theorems. So if we come back and look, when the square of the hypotenuse is bigger than the square of the other two sides, then the triangle ends up being obtuse, right? Because this hypotenuse gets bigger when this angle gets bigger than 90 degrees. So c squared ends up being bigger than a squared and b squared. And again, the opposite is true as well. If we look at c squared and c squared is less than a squared plus b squared, then we end up having an acute angle, right? So if c squared is less than a squared plus b squared, we get an acute angle, and it's not a right angle. And again, we can look at our pencils here. If we come back to 90 degrees, where we started, and we look at the measurement, and then we make this angle smaller. As this angle gets smaller, notice my measurement of my opposite side is getting smaller and smaller. So as this angle becomes acute, this length up here gets smaller. So if we come back here, we can see as what was the hypotenuse when this was a 90-degree right triangle, as what was the hypotenuse gets smaller, this angle gets smaller than 90 degrees. So again, if we find that that length is smaller than what it should be for a right angle, then we know that that opposite angle is going to be acute. So C will be an acute angle. And then the last thing we're going to talk about today before we see some examples is this idea of Pythagorean triples. And actually I mentioned this a couple weeks ago as we were doing some problems because it can be a really huge shortcut, especially when it comes to things like SAT, ACT, SSAT, whatever you might happen to be taking. So a Pythagorean triple is it's a set of non-zero whole numbers that satisfy the Pythagorean equation. So a value for A, B, and C that are whole numbers that when you do A squared plus B squared, you get C squared. So the most common one I think that most people come across would be, this is not the best triangle because I think this is, oh here, let's do this one. This one over here was isosceles. We don't want isosceles. So we'll get rid of the isosceles triangle. We'll look here, and probably the most common would be what they call a 3, 4, 5. And if we do the math here, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, the square root of 25 is 5. So 3, 4, and 5 will satisfy this equation for Pythagoras. So anytime that you have a triangle and one of the legs is 3 and the hypotenuse is 5, you know the other one has to be 4. Or if you have two legs, 3 and 4, you know the hypotenuse has to be 5 if it is a right triangle. Now, this also works for, let's say we make this bigger, this also works for multiples of 3, 4, and 5, sorry. So, if you have 9 and you have 12, well, and we're trying to find the hypotenuse, 3 times 3 is 9, 3 times 4 is 12, so this is just 3 times that length, 3 times that length, and so any multiples of these three numbers are going to work as well. So we would do 3 times 5, which is 15, so x would equal 15 in this case. And you don't even have to plug into the values once you know them. So that can be a real time saver on tests, standardized tests, all that kind of stuff. So those are the Pythagorean triples. And that's probably the major one. There's one more that we'll learn as we take a look at the example here. So they want us to find the length of the hypotenuse, in this case, of triangle ABC. And they want to know if it forms a Pythagorean triple. So we want to use our Pythagorean theorem, a squared plus b squared equals c squared. And we know the two legs. Remember, the legs are always a and b. C is the hypotenuse. So we're going to plug 5 in for a, 12 in for b. You could do it the other way around if you really wanted to. You could plug 12 in for a and 5 in for b, as long as the legs are a and b and the hypotenuse is c. So plug these values in. 5 squared is 25. 12 squared, 144. Add them together. We get 169. Square root of both sides. Square root of 169 is in fact 13. So square root of 169, 13. So we have 5, 12, 13. Now the question is this a Pythagorean triple? We look back to our definition of Pythagorean triple, and it's just three whole numbers that satisfy the equation a squared plus b squared equals c squared. So 5, 12, 13, are those all whole numbers? Absolutely. Do they satisfy the equation? Yes, they do. So I would say that 5, 12, 13 do form a Pythagorean triple because they are whole numbers and they satisfy the equation. And those are the two big ones that I think you should probably know going forward in your mathematical career. 3, 4, 5, and 5, 12, 13 are probably the two biggest ones that come up in things like standardized tests or that would be helpful to you on a day-to-day basis. And it can be helpful. I think I shared with you guys before, but that's how in ancient Egypt, when they built some of the pyramids, that's how they made correct right angles, was they took a piece of rope and they put a bunch of knots in it, and they would take 3 knots, and then they would take 4 knots, and they would take 5 knots, and they would form it into the shape of a triangle, and then they would know that that angle there is a right angle. So it can be useful in certain situations as well. Again, quick checks are for you to do on your own. That's part of the assignment. We'll look over those in class. Next one is just using Pythagorean theorem and finding one of the legs, and then we're actually going to get a little more practice using this simplest radical form. So we're going to do Pythagorean theorem. We know one of the legs and we know the hypotenuse. So we'll substitute 8 for one of the legs. In this case, they do A. We'll plug 8 in there. And then the hypotenuse being 12, plug that in for C. From there we can simplify. We get 64, 144, subtract from both sides, we get 80, square root of 80. Now this is where we need to practice simplest radical form. Essentially what you're looking for is to find two factors of this number 80, one of which is a perfect square, so that we can bring it outside of the radical. Now in this case, the largest perfect square that is a factor of 80 is actually 16, right? 80 is 16 times 5. So with 16 being a perfect square, again, you can separate these two, and we know the square root of 16 is going to be 4. And so we're left over with 4 times the square root of 5. Now, if you didn't recognize that 16 and 5 are factors of 80, you could have done 4, right? It's easier to see that 80 is divisible by 4, and 4 is a perfect square. So once we factor 4 out, right, we would get 4 and 20. And then maybe it's easier to see now that there's another 4 in there, right? So 20 can be rewritten as 4 times 5. And so you have 4 times 4 times 5. Again, these are square roots. That was kind of ugly. Here, let's just move it up a little. So, and then there you have your 4 times 4, or which can be written as 4 squared, and so on, or your 16. So that's simplest radical form, and again, you're going to want to practice that a lot because they like that on the IB test, they like that on SATs and ACTs and things like that. So again, one more quick check for you to do at home, and then the last 2 example problems before we wrap up. This is dealing with what we had demonstrated with the pencils earlier, this idea of the right angle getting larger or smaller and resulting in a hypotenuse that is larger or smaller than it should be. So in this case we can see they want to know, is this a right triangle? Well, we just have to plug in, right, the 2 shorter sides would be the legs, the longest side would be the hypotenuse. So we'll do 4 for A, 6 for B, 7 for C, and let's see if that works. Right? Plug those in here, get 16, 36, 49. That's 52, which is not in fact equal to 49. So we know that this is not a right triangle. Right? The Pythagorean theorem does not work out for these numbers, so that is not a right triangle. They don't ask us if it's obtuse or acute or anything like that. They just want to know, in this case, if it is a right triangle. The next example goes a little deeper and asking if it is acute, obtuse, or right. So they give you 3 numbers again, 10, 15, and 20. and they want to know, is it acute, obtuse, or right? So we can go ahead and plug in what we know. The largest one is going to be C, right? Would most likely be the hypotenuse. And then we can plug 10 and 15 in for the others. We square everything. 100, 225, 400. We add them up. 400 is clearly not equal to 325. So we know that it's not a right triangle, right? We can go ahead and get rid of, right? Definitely not a right triangle because these are not equal. So now the question is it obtuse or acute? And we can see here that the hypotenuse is larger than the sum of the two legs squared, or what would be the hypotenuse, the longest side. So if that's larger, remember going back to our pencils, we said that third side gets larger when the angle that was a right angle becomes bigger. So in this case, the fact that, I better go back to my eraser now. The fact that c squared is larger than a squared plus b squared means that this is, in fact, an obtuse triangle. So the angle has gotten larger, which has made the hypotenuse larger than it should be for a right triangle. So that wraps up 8.1. Like I said, Pythagorean theorem, just a few extra applications that you might not have been used to. So go ahead, wrap up these quick checks, and we will work on this a little more tomorrow.